So today we're going to talk about square root functions and inequalities. And so this is going to be another one of your parent functions. And so this year we've talked about parent functions that are lines when we just have y equals x. We've talked about the quadratic, which is always going to be a parabola, and we talked about how to transform that within the coordinate plane. And so now we're going to move on to square root functions, and we're going to graph and analyze square root functions, and we're going to graph square root inequalities. So new vocabulary for you will be square root function. And square root function, our most basic square root function, is simply y equals the square root of x. That's also considered to be a radical function, although radical functions can get a lot more complex than this. And a square root inequality, an example of this might be something like y is less than the square root of x. So let's look at our parent function, f of x equals the square root of x. And so here it lists the domain and the range and the intercepts, but we're actually going to look at how we're getting these. If we have x and we have that the output, or f of x, equals the square root of x, you got to be smart in how you choose things to put in your table. First thing you need to recognize is that underneath a radical, we can't have a negative number because that's not going to show up in our coordinate grid. And so think about the smallest thing that you could have underneath that radical, and that's going to be 0. 0 is fine because we can say that the square root of 0 is 0, and that's our first ordered pair. The next perfect square, now let's talk about what perfect squares are. Our first perfect square is 1 times 1 is 1. Our second perfect square is 2 times 2 is 4. So 4 is a perfect square. 3 times 3 is 9. So these are all of our perfect squares, and we want to think about what values, how we can get those values underneath the radical. So if x equals 1, that's a perfect square, and our output would be 1. Our next perfect square is going to be 4, and because the square root of 4 is 2, so this is now changing the shape of our graph. What's our next perfect square? Well, over here we have that our next perfect square is 9, and if we plug in 9 for x, we get the square root of 9 is 3. And so our parent function starts here at the origin, and it curves up ever so slightly, and just does like a half of a parabola. Now it's good for you if you memorize the perfect squares at least through 169. So they go 1, 4, 9, 16. My pen can't keep up with me. 16. It still isn't keeping up with me. 25, 36, 49, 64, 81, 100, 121, 144, and 169. These should all be perfect squares that you recognize immediately as being a perfect square. Oh, going back, looking at the domain and range of this, our x values begin at x equals 0. And so our domain is anything where x is greater than or equal to 0. Our range starts at y equals 0. Anything above that y-axis, including that y-axis, is part of our range. And so we have y is greater than or equal to 0. So identify the domain and range of f of x equals the square root of the quantity x minus 2. Let's go ahead and put a graph on here to see it. And let's do a t-chart. So for this t-chart, what's going to give us a value of 0 is our radicand. And if x equals 2, that means that 2 minus 2 is 0, and the square root of 0 is 0. So we're trying to pick values of x that are going to give us those perfect square values, or 0. So the next thing we need is our radicand is 1. Well, what value of x is going to make this radicand equal to 1? If x is 3, then 3 minus 2 is 1, and the square root of 1 is 1. The next thing we need under here is 4. And if we put in 6 for x, 6 minus 2 is 4, and the square root of 4 is 2. Notice how the y values are all going up in consecutive integers. So we're going to plot these points, 2, 0, 3, 1, 6, 2. And we have the same shape as our other function. It's just moved to the right 2 units. And this is what we talked about when we did quadratics. When it's within that function, we have the quantity x minus 2 that shifted it to the right 2 units. Nothing has changed about the shape of our parent function. And now you're seeing all those variables again, the a, the h, and the k. And these are going to have the same effect on this function as they did on our parabolas. K is going to shift the square root function up and down. H is going to shift the square root function left and right. And A is going to be our vertical stretch or shrink to the function. So let's look at what's happening with this. We have y equals a times square root of x minus h plus k. So in analyzing what's happening here, we have x minus 4. That means that h is equal to 4. And this means that it's going to shift to the right 4 units. K is 2 in this case, and that means it's going to shift up 2 units. Now those values just gave us the starting point, or you can see it as the vertex of the square root function. So it went to the right 4 and it went up 2. That's going to be our starting point. Now what happens with that 3? It's stretching it. So if a equals 3, we have a vertical stretch of 3. If we go back and we look at these first functions that we graphed, between the vertex or the starting point and this, it was always up 1 over 1. When a is 3, that means that this is going to be vertically stretched by 3. Now it's going to go up 3 and over 1. But let's go ahead and pick some ordered pairs to see why that is. What's the best value to pick here to start for x? We want that radicand to equal 0. So we're going to first plug in x equals 4. So 4 minus 4 is 0. Square root of 0 is 0. 3 times 0 is 0. Plus 2 is 2. And that's how we got that starting point. Next value we want to pick for x is what's going to give us that square root of 1. And if x equals 5, we get 5 minus 4 is 1. Square root of 1 is 1. 3 times 1 is 3, plus 2 is 5. And so we have the point 5, 5. And that gives us the shape of this function. And it's going to be really tall. And it'll keep going up like that. The next value of x we'd pick, and it's not going to fall on this graph anymore, is what's going to give us a value of 4 underneath that radical. If we plug in 8 for x, 8 minus 4 is 4, square root of 4 is 2, 3 times 2 is 6, plus 2 is 8. So the point 88 would be up here, and it would go through there. So very tall. And that's it for this section. You should be able to do the homework now.